Okay, so this is the second module of lecture 13, convolution neural nets and image classification. Very important. So we actually talked about this back probe, right? So you can think about all the deep learning modules from a block view. And then as long as they're differentiable and it can pass the output to the next layer, it can also accept the gradient from the next layer and also pass the generated revised gradient to the previous layers. This is actually shows by this figure. So every block, you need to be able to pass the y to the next layer. It also needs to be able to accept the gradient from the later layer, and then doing a multiplication chain rule type of operation, generate and this gradient that I can pass to my previous layer. And then you're fine. You can just do all these different kinds of composition of different blocks. And this is really similar to Lego building. And so one of the almost the most important block for vision tasks is the convolution neural network, or maybe convolution blocks. And this was invented by Professor Locality in 1998. And this is almost the first neural networks back then trained with many layers, multiple layers. And the fundamental idea actually totally captured by this image. This 3 image. So the bird just flies, and it doesn't matter where it appears in this image. It's always a bird. And I really don't need the whole thing to understand that's a bird. And the signal is very local first. That's the first signal I want to emphasize. So I want to change to red color. So the bird is a very local signal. So that's the first you have to keep in mind. When do image recognition, there's many of those local signals. They're much smaller than the image itself. And also, it doesn't matter that small part really is. It's always about image, about a bird. So the whole convolution neural nets, the idea is exploitation of this intuition. So first intuition is the objects tend to just have a local spatial motif structure. And I don't need the whole image to recognize that's a cat. I don't need the whole image to recognize that small part is eye. And it's just very local. The second is, it doesn't matter that bird really is in the whole image, it's in the upper corner or lower corner or in the middle, it is still a bird. So this is called translation invariance. And object appearance is independent of the locations. So you can think about convolution neural nets, it's just model exactly local motif patterns that is translation invariant. Yeah, that's a quick summary to talk about convolution layers. And then, in fact, it's not just vision has these properties. And as long as your data is followed this type of largest type of property, like audio data, especially audio data, and you can use convolution blocks to analyze that type of data. All right, so to be more concrete, and we're going to have much more detailed explanation later. So what do we mean locality is, so rather than learning the weights to cover all the image, every one of the pixels, we only cover those local windows. And the other is this translation invariant is, so rather than using different weights on different parts, I'm going to use the same weights to detect that type of windows. So this is called a sharing weights trick. So it will be much more clear later. Okay, so convolution neural nets starts from this 1998 LearnNet. The first is called the LearnNet. It was used to recognize handwritten checks. And then in this ImageNet competition, the AlexNet is the one. It's a deeper model. And then later people just keep pushing the to make it better and better. So this is the 2012 AlexNet. It has only 8 layers, and then later people improved it into another 8 layer. Then this is the VGG19, and then Google pushed it to like 22 layers. And then in ResNet, this residual trick, it's a really big breakthrough in making the convolutional networks deeper. That trick makes you can train like hundreds of layers. This is the ResNet 152, and but they're all like the fundamental important blocks are convolution block. Okay, so this figure I always like to show it is this is actually old. I think this is before 2017, but it's a good figure to show you the scalability. So you can think about this x-axis is cost in terms of time cost. We can think about this like time. This is the time dimension, and then the y is the accuracy, is what the prediction. There's also the circle size is the memory cost, right? You have to save it somewhere. So this is a space cost. So this figure summarized time cost, space cost, and also versus the prediction performance. So the VGG, I mean, you can actually tell this group, it's actually pretty costly. They are large and also takes more time. Their performance, it's almost in this bounded about 75 around that time. And then ResNet, so ResNet 34 is the one I used. ResNet 34, and it's actually pretty small. I mean, in terms of the size, space cost, and also time cost. The prediction performance almost as good as this really humongous VGG models. So it's just, you can actually tell, even though they are all fundamentally are all convolution architectures, but there are a lot of engineering details. Yeah, so in this deep learning field, details, the devils is in the details. That's really true, that phrase, yeah. Okay, so let's see what is convolution neural net and why convolution neural nets for the images. So now you have an image like a cat, I mean, or maybe the X shape I gave you, which is like this 1, 0, there's 6 in that representation. I just give you 9 features, right? So it's X. If you remember that X shape, it's really just you can just concatenate it, make it a long vector, and that give you a representation. And then you can just use our the perceptron. This is a logistic regression, linear multiplication plus a sigmoid layer, and then it just totally projected into the next layer. This is actually called a dense layer in the KRS. And this type, we covered, this is the MLP structure, right? All right, so we can actually just hopefully, because it just gradually project your images into higher order representations, and then hopefully it can predict this is a cat. So, but in fact, I mean, because of this locality and translation invariant property, we actually can simplify this fully connected layer-to-layer projection into much simpler and much smaller weight. So let's see how to do it. So again, the property is the locality. So first, the locality is just we show you this bird, and then let's see actually the part of the bird. We're having this neuron hopefully trying to detect the beak of the bird. This neuron really doesn't need to see the whole image to discover the pattern. It can only just need to see a really tiny window out of the image to know that's a beak. Everything else, it's really irrelevant, to be honest, right? And so we can think about there's a beak detector, and then it can detect beak, and it only need to see the local smaller windows. So that means we need some kind of small window type of detector. So that's the first design. This type of window detector only just need to connecting to the smaller regions with less parameters because it's much smaller. Right? It's not the whole image as input. It's only just one tiny part. Okay, so, and the second property we actually said, right, that bird can happen like in the left upper or maybe lower right. I mean, it doesn't matter what that bird really is. It's always a bird. And then we can just, like for the beak case, it's the same. So for this bird, it's actually in the upper left corner. And for this bird, that beak is in the middle. But it's always just a beak detector. So I should actually use the same detector, no matter that smaller window is in this whole image. So they do the same thing. So which means what? When I'm applying this beak detector, I should use the same detector weights. So that's exactly people do. They just use the same set of parameters. It doesn't matter this parameter window parameter is applied in the left upper corner or is applied in the middle. It's the same set of weights. Okay, so and then third property I did not cover, actually it's also very important for the image classification, is something called subsampling. So for the bird, I actually can just reduce the image resolutions. That's still a bird. It's just the part of the image property itself. And we can actually, in fact, rather than keep every pixels, we can figure out the way, only leave the important signals, and then we subsample, and then to make the image much smaller. When you have a smaller X, you have a smaller number of parameters to estimate. And that's the essence. So, okay, three things combined together: local, translation invariant, and also subsampling. Okay, then that's exactly how the CNN really worked. So you have a convolution layer, and to handle that locality and translation invariant, you have max pooling to handle that subsampling. And you can repeat this again and again, and to make it really, really deep. And for the final output, you just concatenate it, make a vector that's called a flatten layer. And then you just feed into this MRP, which we actually used before. We showed you before, and then to perform classification. And that's the whole pipeline of this most simple convolution models. And so let's see, the property 1 is the locality, right? Property 2 is this translation invariant. And this property is captured by the convolution layer, convolution block. And the third property is captured, implemented by the max pooling blocks. All right, so let me give you now a very concrete example, just this X type of. So this is my image. I simplified it into only 0, 1 in each of the pixels. I'm trying to detect what? I'm trying to detect other like shapes like this. For example, yeah, so I'm trying to detect this kind of shapes. So in fact, if that's what you want to detect, and then you can just, now I'm just using my eyeball, right? How do I design a detector to detect this kind of cross, right? Actually very easy. I just design a detector that all this diagonal term is 1, everything else is -1, which means if the diagonal is 1, 1, 1, I like it. If everything else is actually not, it has some numbers, so I prefer like this are all 0, which means if there's any numbers in the off diagonal, I penalize them. That's exactly this filter really is. So when it cannot highlight, it's firing during for the diagonal term, it follows my pattern. For the off diagonal term, I prefer 0. For anything else, I penalize it. That's my filter 1. And for the filter 2, I prefer this kind of 1 shape, only in the middle. If it's 1, it's fired in the middle. Everything else, I penalize. The 2 sides penalize it. that's really just this filter, assuming you know this filter, and the two perfect filters. And then let's see when we apply this filter on my image, that's actually my detector, right? So what happened? So this type of filter is actually, the size of the filter is exactly the kernel size you need to decide in your convolution unit, like the parameters. So for the first filter, I just apply it. It's a sliding window operation. If stride is 1, because I'm sliding with overlap operation, right? I only just jump 1. So that's called stride equal to 1. So for the first position, because that's exactly matched me, right? Matched my filter. So this really fired, give me 3. So in fact, it's just an inner product, right? It's very easy. It's an inner product of this matrix and the window matrix, the window I just extracted from my current image. Yeah, so you just keep applying, and until the end, it give you a full, like that inner product operation results. All right, so this is how you get from applying the first filter. And it's actually, the pattern is really clear. The largest number is this 3 and this 3, because this block and this block matched my filter. That's exactly what I want to detect. All right, so this is detect 1, and then you can do the same thing for detector 2. And the detector 2 is looking for the pattern like this, right? Same thing. What you going to get, you just apply this in the product operation. What you're going to get is there's only one fire, because there's only one matched my detector 2. And by this way, you get the feature map from the first detector and another feature map from the second detector. Each feature map generated, so by a specific filter, it's almost like a smaller image. It just converted by conversion represented by that filter. And this, every position here still keep the spatial relationships. So like this, first this -1 here is on the left. So this is representing the left upper corner, and the 3 representing the lower right corner. So this kind of convolution operation still keeps the spatial relationships between the windows. So this is extremely important. And let's then take a look. So what's the differences of this convolution block application versus a fully connected application? So we actually can just see, when you apply this fully connected convolution, you just concatenate all the pixels into a very, very long vector. So this is the lower half panel trying to represent, because this figure, this image is a 6 times 6 image, so which generated like 30 vector of 36 size. And then you just try to convert it into a dimension, like for example, h. So h size, then essentially, and the p equals to 36. We are right here. So this weight vector w, you need to like converting from the p into the h should be a p times h conversion, right? Because you have so to convert a input dimension that is like p dimensional to project it into h, and this matrix needs to be p times h. And then let's look at the upper convolution. The upper convolution, it's different from this, and it's just apply this window-based smaller w on top of all the possible windows that filter can be applied upon. And this w itself already represented, it's actually very small. So one is, each one of them is 3 times 3. So each of the WS is just 3 times 3. And let's see if we think about it. The upper convolution generated, it's actually generating a much bigger vector. So this is almost the same size as your original image. So in this case, actually you are generating a 4x4 feature map. It's just because your original 6, your kernel size is 3, and then you can apply 4 times this kernel size 3 window, and then this gives you a 4x4 feature map output for each filter. All right, let's just then see, to summarize, in the convolution way, uses only 3 times 3 times 2, 18 parameters. These fully connected multilayer perceptron way, because assuming we have 2 filters, means the same thing as above. We try to generate 2 different kinds of outputs, so channel 2. And then that means it's the same as the previous figure. I set h equals to 2. And then the lowercase needs 36 times 2, actually 72 total parameters. It needs much more parameters, but seems to keep much less information because there's only 2 outputs in this type of formulation. And then let's just look at it even more concretely. All right, so we're applying this 3 times 3 filter on my 6 times 6 image. And then I'm applying it the first time at this upper left corner. And then essentially it just, this W filter is doing this inner product with only a smaller window at this red panel it shows. It's an inner product operation. It gave me 3 output. And if I'm showing this as this multi-layer perceptron way, what it's corresponding to. So essentially, I'm just writing out the full 6 times 6 image into this 1, 0, 0, and then you can tell the first pixel, and then second pixel, and the third pixel, they are the 1, 0, 0. And then because the first 6 is the first row, and then 0, 1 is starting from the second row, and then 13 is in fact the third row. So by making this into a row form, like the tabular form, we are losing out neighborhood relationships. This is one thing, right? So which makes kind of image is very different from the tabular, because there are neighborhood relationship there. So this is the first thing we want you to pay attention to. And then let's see how this 3 is generated. So essentially, I still just have this W, like it's a W vector, right? I can think about that as a W vector, generate a 3. And this W vector, it's exactly equivalent to only those connected to in the windows, and there's a number, and everything not within that window is 0. So you can think about it that way too. So this will try and show this W, like S1, it's only connected to so this first position is 1, 2, 3 in this vector, and the second connect to the 7, 8, 9, and then it connect to the 13, 14, 15, and then it only connecting to this 9 points if we treat this through this multi-layer perceptron type of thinking. And it's only connected to only 9 out of the 3 points. You can think it's connecting to 9 pixels or 9 features out of the 36. 9 out of 36. Yeah. So, and it only connects to 9 inputs. And then when I'm applying the same operation by sliding the window, what does that mean connecting to this kind of multi-layer perceptron view? So I'm trying to apply this filter to the second sliding position by just sliding my window to the right just for one step, 1 pixel size. And then it essentially generating -1. And rather than using different weights, I'm using exactly the same weights as the filter 1. And it's generating, if you think about this is the hidden dimension in this second layer, this generating a different output, but using the same weights as the previous weights I used for generating the 3. So this is the share weights, how the share weights is implemented, and then that's trying to capture the translation invariant properties. Okay, so in the end, to generate this really big, like 4 times 4 feature map, I do not need this 36. So if using this multi-layer perceptron way, so we can think about this as a hidden dimension with 4 times 4 outputs. So if using the fully multi-layer perceptron way, we need to have this P equals to 36, H here equals to 16. We need to have a 36 times 16 like weight matrix to implement this using the MLP way. But using the convolution neural networks, we only need a 3 times 3 size parameter weight matrix. So this is extremely efficient, parameter efficient, and also capture the intrinsic properties of the image recognition task, like the translation invariant and the locality properties. Yeah, so this is really the essence about the convolution block. All right, so let's come back to look at this whole convolution neural network model architecture normally. So you normally have convolution, then max pooling, then you can repeat this repetition many, many times. And then you just, for this output, you flatten it and then feed into a fully connected multi-layer perceptron network. Then in the end, normally people, if it's a classification task, multi-class classification task, you're going to have a soft max layer and then generating the Y outputs. All right, so we already explained very carefully of this convolution block. Now let's see what is max pooling block. So the max pooling block actually has no parameters. So this just to show I applied the filter 1. I converted my image into this 4 times 4 feature map. And then that's for the filter 2, I also applied it and generated 4 times 4 feature map. And then I can just, assuming I'm using a 2 times 2 max pooling, which essentially means I try to summarize a 2 times 2 smaller window into one number. So this within that smaller window, again, a sliding window operation. I just, within that window, I do a max. Within this window, I do a max. Every possible window, I do a max. And this is the operation of max pooling. And if you think about it, so this trying to highlight the signals, because what is my signal, what I'm trying to do with the filter 1. In filter 1, I'm trying to capture those this kind of cross shape. And after this max operation, this 3 and 3, if you still remember that image we tried to apply, and that has this block in the upper and lower, and the 3 exactly memorize it. The max operation highlight the more important signals and removing the less important signals. And then similar for the filter 2, when you do the max, and this in the original figure and original image, then that lower right one shape, it's also got highlighted. So which is exactly this filter 2 trying to capture. It's trying to capture this kind of a vertical one shape of the signals. So this is really nice, and it gives me a smaller image essentially. So if you think about it, and after max pooling, I got a 2 times 2 image, but keep the signals very nicely, and it matches the spatial relationship. It keeps the spatial relationships among these different windows too. All right, so let's come back to see to put convolution and max pooling together. So my raw image is this, and then it has the signal like that. And after the convolution and the max pooling, this gives me two channels. One channel is the red channel, the other channel is the blue channel. In this red channel, I actually know the good signals in this on the two left windows, and then on the second channel, I know in the lower right window, I have a good signal detected by my filter too. So yeah, you can think about this as just a new image with a smaller and also a more sharp signal got detected. And we can think about each filter. So in this case, there are two filters, and then there's two channels representing my current new image. So just repeat what I tried to draw. And then now let's just see this whole thing together. After one convolution and max pooling, I got a new image. So this repetition of this block will give me a smaller and sharper new image. The number of the channel is the number of filters. So, and also if your image, so what I showed you before this black and white image, there's only one representation. I mean, it's the image raw representation, it's just W times H, right? So in the black and white case, what your image really were, it's just a W times H matrix. So that's a black and white case. But the colorful images, they have RGB channels, right? So this makes the input, it's not a matrix, it's a tensor. And then you just really, what your filter design needs to consider the channel too, which makes the two filters, while you have 3 channel input in the raw, and then my filters also had that 3-dimensional channel represented. And then you just convert it into this H that you designed. In this case, there's still just the H, the number of filter is 2, so which makes my output images is a 2. In the first, after first convolution and max pooling, in my newer image, my channel size is 2. It's actually decided by the filter size. As a designer, you decide. All right, so then let's sort of take a look at the flatten layer. So the flatten layer, essentially, it's very, very simple. I'm just concatenate by removing all the spatial relationships, and also by concatenate all the filters, all the channels. So in this case, I have the red channel. The red channel created a vector, and the blue channel created another vector. You can just concatenate them together. And inside each channel, you just concatenate whatever pixels or that windows, and you make the whole thing as a vector. And then this gives me an 8x1 vector to summarize the whole representation of my image. And I can just feed it into feed-forward MRP network and try to capture the signals, what type of this 8-size vector representing the signal that I care. Maybe is this an X, or is this not X? Is this the Y, or is this not Y? So here I try to just give you an idea. I mean, one of the things very importantly you can tell is, how do I know how many filters, right? And if you think about, I mean, we said, I mean, this first filter trying to capture this more like this left to the right, left upper to the right lower cross, that stroke. And then this filter 2, trying to capture this from the upper to the lower, this perpendicular stroke. If I want to capture Y, just intuitively, I think I can just design another filter. So this is really just eyeball. So I can just design another filter that capture this right left to the lower right upper to the lower left, and then everything is those I like is 1, those things I do not like is -1, and I can think about this is more like my filter 3. Yeah, so and I think this should be enough, at least for the first layer, to detect my Y, right? So really, how many filter, this is filter 3. So really, how many filters do you need? It depends. There's no like generic numbers that works for everything. It depends on how complex your image really is, and the fundamental task you try to solve. So because this one is so simple, so that's why maybe 3 filters is enough. And when you have much more complicated, like maybe even the digits itself, if you think about it, it's much more complex than this Y, right? How do you detect a 8? How do you detect maybe a 2 or 3? So that's the number of filter is something depending on the task, depending on this domain itself. All right, so now let's see some kind of a little bit code. So the very simple. I mean, you just convolution 2D in the keras. I mean, you specify the filter size 25 here, and then use the kernel size 3 times 3, and then the input shape is a 28 times 28, which is the simplest MNIST hand digit recognition images. And then you can add max pooling, and this generate. So before the max pooling, the convolution using that 3 times 3 kernel generate a 26 times 26 like sliding window output. This is the feature map output. So it's very similar as what we show you. So in the one we show you is a 6 times 6 using this 3 times 3 like kernels. We got a 4 times 4. And here is 28 times 28. We apply 3 times 3. It gave me 26 times 26. And then in the previous, we use filter size into equals to 2. Here it's a much bigger filter size, which is 25. The filter size, and then you can do max pooling because it's divided by 2, right? So and that after max pooling, you're getting this 13 times 13. And then similar to the example I show, we got the 2 times 2, so much smaller image, and you have 25 channels. So for each filter, you have a smaller image, 2 times 2. In this one, 13 times 3 times 13. And then you just do another convolution, and it's still 3 times 3. And this time, actually, this increases the filter size from 25 to 50. And then you do max pooling from 11 times 11. You get smaller image 5 times 5, but each smaller window is represented by 50 size filters, channels. And then you can actually calculate at each layer what are the number of parameters that need to represent that. In fact, this is actually pretty easy. So that's 9, and this is also 9. I believe, sorry, and then you flatten it. So after you flatten it, so because it's a 50 dimension and then 50 dimensional filters, in each channel, there's a 5 times 5 small image. So in total, you just concatenate across the spatial position, then across all the filter, all the channels. You got 1, 2, 50. You got a vector with 1250 size, and then you fit into MLP. Then in this case, it projected it into 100 first, and then from 100 project into the 10, and then predict, because this one is handwritten digits classification. So the number of classes, there are 10. So that's the reason why this is like a 10 here. Yeah. All right, so this is almost like you need to implement your homework. Yeah. So the fast AI, it's also very similar. So you can try this, and you can also, I recommend you to try to use some existing structure, which is much more complicated, but it's not as simple as what I showed in the previous page. You need to learn a little bit how do you adapt those really big models trained on the ImageNet, like shows here. For example, ResNet 34 is the one I used to show you, like in our COVID-19 CT scan classification. And there's also ResNet 101, there's Inception, and there's all these different kinds, very easy to be loaded from the Keras model zoos, the fast AI, the model zoos. So, but you need to consider when you're doing the homework 3, I mean, is it fact? Do I have enough like computer architecture to support that type of training? It's also pretty large. This kind of model is also pretty large. And also this is just like, I think this figure, I got it from 2017. And now there's really big, big efforts by industry and also by a lot of research labs. I mean, trying to make those big models to be smaller and push them into the edge computing. So for example, I got this figure from the Google AI lab. So they are trying to highlight something called EfficientNet. And it's much smaller in terms of the space cost, but the performance-wise seems to be very impressive. Look at this red line. So there are a lot of existing model architecture you can borrow, and that goes much more beyond from the basic convolutional neural network we introduced you today, but I just strongly recommend you to play with it, because this is state of the art, and this type of learning will benefit you a lot if you like the vision data. This is all I want to talk about convolutional neural nets, and I'm going to stop my recording.